Hello, welcome to this presentation on fatigue and recovery. Fatigue can be defined as extreme tiredness resulting from mental or physical exertion. There are two different forms of fatigue, physical and mental. Physical symptoms include reduced power and slower reflexes, as well as sore or aching muscles, chronic tiredness or sleepiness. Mental symptoms, on the other hand, are less obvious but include slower decision making, unrefreshing sleep and impaired memory. These can be displayed within different sports and can affect performance. Causes of fatigue include dehydration, inadequate recovery periods. These can be short-term, for example, in between sprints and interval training, or long-term, for example, between training sessions. Another cause can include inadequate carbohydrate consumption. This can lead to effects such as ones that were mentioned below, like a decrease in performance, reduction in power, and lack of accuracy. The physiological causes of fatigue are the fact the body needs to resynthesize ATP, running out of energy sources, a build-up of waste products such as lactic acid, neuromuscular functions, and the need to control our body's temperature, which is known as thermoregulation. Different forms of fatigue can occur depending on the intensity and duration of the event. Also, different activities can affect different athletes in different ways. A muscle contraction is also a factor, as, for example, eccentric contractions are much more tiring and much more fatiguing. These generally occur in weightlifting, and, for example, and other examples like squats. We can use these criteria here to analyse fatigue in different sports. So we'll do this using type of activity, energy system used, muscle fibre type of muscle contraction, intensity and duration, and level of fitness. For shot put, we use the ATP system and fast glycolytic fibres, which use an anaerobic source of energy. These fatigue much more rapidly, so cause more significant fatigue and quicker fatigue. This event is short duration and high intensity, and also intermittent, so there's rest periods between throws. Low levels of aerobic fitness are needed, but high levels of muscular power. And due to the high level of power needed from the event, arm muscles may fatigue, so shots become less powerful. However, there won't be so much of shortness of breath. Next 100-metre sprint is a continuous event and uses the ATP-PC system. Depending on the athlete and depending how long the sprint takes, you may break into the lactic acid system. It also uses fast glycolytic muscle fibres, which have a high contraction time and high force production. It's a high intensity, low duration event, hence the muscle fibre type, and it needs more power rather than being able to go for a long time in terms of fitness. So you may suffer from muscle fatigue due to the high intensity. 400-metre sprint is also continuous and will also use the ATP system, but will also definitely use the lactic acid system. Fast glycolytic fibres are used for 400 metre and activities like this, as they involve high speed, strength and power. However, they won't be as powerful as a 100 metre sprint, as your body can't keep up this intensity. It's high intensity with slightly longer duration than the 100 metre sprint, and a high level of fitness is needed to keep power going, as the body will undergo muscle fatigue and lack of breath. Next is the 1500 metre event, which is continuous, and we'll go through all three energy systems, so we'll use ATP, PC, lactic acid and aerobic system. This is a high duration event but fairly low intensity, so your body will use oxygen for this event. You won't feel the same burning sensation as 100 metre sprint or a 400 metre sprint, and you'll be able to go for longer. And finally, this is the same for the marathon. Again, you use the aerobic system and you'll be able to go for a long time. In terms of types of fatigue, there are three different types of fatigue: localised, general and chronic. Localised occurs in muscles from repeated contractions without recovery. This type of fatigue may be experienced when doing bicep curls with the fatigue in the biceps brachii. Also, within the examples, it may be experienced in leg muscles in the 100 metre sprint. General fatigue occurs post-training and involves feeling physically or psychologically weak. And finally, chronic fatigue can be caused by lack of sleep or overtraining. This can result in a weakened immune system. And finally, lack of recovery can cause this and means you may not be able to fight illnesses. Moving on to maximal exercise. Characteristics of maximal exercise include neuromuscular recruitment of fast glycolytic motor units, fast reaction times in high intensity exercise. In a sprinter, muscle mass is predominantly composed of fast glycolytic fibres, which cause you to have a high force generation. This type of activity uses anaerobic energy systems such as ATP-PC system, which means the body uses PC and glycogen stores. As the lactic acid system can be used, lactic acid will be produced, and events that use maximal intensity exercise in order to compete will have generated intolerance of acidosis or buffer capacity. In terms of metabolic responses, high intensity exercise causes a much quicker depletion of ATP and PC stores compared to slow oxidative fibres or events such as 1500 meters or marathon. This is due to the intensity and power generated from the start. This type of activity also needs energy quickly due to the quick starts and fast reaction times. After maximum exercise, PC stores can take 120 seconds or longer to be restored. Furthermore, high intensity exercise reduces glycogen content significantly. This is because glycogen is readily available and used for energy production as part of the lactic acid system. In this, the glycogen is turned into pyruvic acid. Muscle levels, in terms of PC stores, muscle levels can be almost completely depleted after maximal exercise, especially in exercise that lasts longer than 10 seconds, as the PC system can work for up to 10 seconds, and we can see this from the graph. This depletion leads to the rapid decline in power output observed during maximal exercise. As we can also see from the graph, PC recovers fairly quickly, and around 300 seconds after exercise, PC stores have almost completely recovered. As people who use maximal exercise events need high levels of PC in order to generate the power. So these athletes may want to improve their PC stores, which they can do using PC supplementation. However, this can have nasty side effects. In this EPOC graph, which stands for excess post-exercise oxygen consumption, which is the extra oxygen consumed or used above resting levels in recovery, and can be recognised in someone when they're breathing very heavily after exercise. We can see this for maximal exercise on the right here, and at the start they are not in steady state exercise and go above the VO2 max. Therefore, they are using more oxygen than they are consuming, which causes an oxygen deficit to be produced. An oxygen deficit is defined as the amount of oxygen failed to get on board during the event or exercise, and is similar to oxygen debt, which is defined as a temporary oxygen shortage in the body's tissues arising from exercise. Once exercise is finished, there are two types of recovery that can occur alongside each other. Firstly, you have the fast component of recovery, or alactic recovery, which occurs 2 to 3 minutes after exercise is finished and requires 3 to 4 litres of oxygen for it to be completed. This is displayed as fast and deeper breathing and has two main functions. Firstly, this type of recovery involves resynthesizing ATP and PC stores, and secondly, it also replenishes the myoglobin stores in the body. Also in maximal exercise, the oxygen required for exercise is significantly higher than in submaximal exercise and causes a much higher oxygen deficit. This is because the anaerobic system is predominantly used for energy production, which means the body can't use oxygen to generate this energy, which results in a higher oxygen debt. In short duration activity, there isn't much chance for the build-up of lactic acid, so the slow component of recovery may not be as long as in other sports. And during the second part of recovery, known as lactacid recovery or slow recovery, the lactic acid is oxidized or removed. 65% of the lactic acid is converted into pyruvate and enters Krebs, therefore as a fuel to make energy, and is ultimately converted into carbon dioxide and water. 5% is converted into glucose and 20% into glycogen and stored in the liver due to the Cori cycle. In the Cori cycle, glycogen is converted into glucose, then pyruvate before turning into lactate in active skeletal muscles in a process called glycolysis. This lactate is then converted into pyruvate, then glucose again in the liver in another process called gluconeogenesis. The final 10% of lactic acid is converted into protein, and this overall process can take up to 2 hours. Furthermore, during lactic acid recovery, carbon dioxide is removed and muscle glycogen levels are replenished. This overall process can take up to 2 days. Finally, there are adaptations for athletes who compete in short duration, high intensity events such as sprints. For example, they have an increase in sodium and potassium ion regulation, which controls impulse transmission. They also have an increased buffer capacity and an increase in glycolytic enzymes. Additionally, they have increased oxygen, VO2 max, and muscle oxidative capacity, which is the activation of the CV system and cardiac output in intensive exercise. In moderate intensity and moderate duration exercise, such as the 800 metre event, in athletics, the athlete competing in this event will use the ATP system and then the lactic acid system. This system breaks down glycogen, which does cause stores to be depleted. This is the fuel of the system. It is broken down into glucose, then pyruvic acid, when there is no oxygen present. And when there is no oxygen present, it causes lactic acid to be produced. If the event lasts longer than around 2 minutes, then the body will start to use the aerobic system, and therefore oxygen is being used to produce energy. As a result of the production of lactic acid, levels start to build up in the blood and at some point will reach its lactate threshold. This is defined as the exercise intensity at which the blood concentration of lactic acid begins to exponentially increase. It can also be defined as the point during exercise of increasing intensity at which blood lactate begins to accumulate above resting levels, and is where lactate clearance is no longer able to keep up with the lactate production. During low intensity exercise, blood lactate levels remain at or near resting levels, but as intensity increases, there becomes a break point where blood lactate levels rise sharply. At your blood lactate threshold is when you feel a burning sensation, but at this point you're still able to function, however your energy is limited. But if you keep pushing further and after further effort, you will reach a point where you can't work anymore, and this is known as your OBLA, or your onset blood lactate accumulation. This point generally occurs when your blood lactate levels are 4 millimoles, and this results in fatigue. Elite 800 metre runners are trained so that their pace at 4 millimoles is as high as possible, and they don't cross this point. This point is much more delayed compared to a sprinter. So a sprinter their OBLA would be about here, but an 800 metre runner is much further along. These athletes aim to maintain this pace till the end and cannot fatigue early on in the race. The faster the pace without fatiguing, the better they will be at their event. And although we see lactic acid as the factor that causes our fatigue and decrease in power performance, it is not in fact the lactic acid that causes it, it's hydrogen ions that are bad for the body. The hydrogen ion is what causes lactic acid to be an acid and is it's what causes it to be an acid. It interferes with electrical signals in your muscles and nerves and slows energy reactions due to enzymes. It also impairs muscle contractions. The burn you feel from intense exercise is in fact hydrogen ion build-up and not the lactic acid. As they are very acidic, a build-up can cause a decrease in pH, and as enzymes have very specific conditions in which they work, e.g. a pH of 7, then it can cause enzymes to cease functioning, potentially denature. Specifically, it's the glycolytic enzymes that are affected, which causes energy reactions to be slowed. EPOC has